First of all, I would like to say that I am happy to be here in this great conference, and present a paper in front of such a great people and great engineers like you. And also, I would like to thank the chairs of this conference, Dr. Professor Abdullah and Dr. Jumana, for having me do the presentation. Okay. First of all, I would like to introduce myself. My name is Engineer Basil Al-Khamis. Okay, I am from Malta University. I have a master's degree in smart grids and electrical power systems. And this paper is part of my thesis, the application of adaptive control to enhance power system stability using virtual synchronous generator, under the supervision of my great Professor Abdullah Denat. And before I start, I also would like to thank all my professors in the electrical engineering department at Malta University, and one of them is Dr. Ziad Majali. He's sitting here in this hall. Okay. So the title of this paper is the application of synchronverter for the enhancement of power system stability. The contents is the research problem and introduction, synchronverter structure, results, conclusion. Research problem statement. Okay. If a large disturbance occurs within the system, like the loss of large generating units or severe fault scenarios, the system could suffer from the rotor angle, frequency, or voltage stability issues. In this study, an approach is proposed to improve the transient stability of the power system based on the application of the virtual synchronous generator. Later in the slides, I will explain what is the virtual synchronous generator or the synchronverter. Okay. The synchronverter can be considered as an inverter, but with a special function. It can operate like a synchronous generator to produce a virtual inertia to stabilize the system, especially in the cases where the renewable energy sources are highly integrated with the system. The synchronverter circuit can be considered as an equivalent circuit of a synchronous generator, but with the capacitors of small value that are shunt connected with the stator terminals of the generator. What is the importance of the study? The importance of this study is that we all know that the increased penetration of photovoltaic panels in the power system will decrease the overall inertia in the power system due to the absence of rotational masses in the static inverter. One of the major problems that is caused by the lack of inertia in the power system is the transient stability contingency. Introducing a method to enhance the transient stability margins for the power system whenever a lack of inertia case happens within the system is crucial, because the operators cannot deal with the transient contingencies because it is in millisecond range. So here in front of us we have, let me bring the pointer. Okay, here we have the three-phase inverter, which have the three legs universal bridge, consisting of 6 IGBTs, insulated gate bipolar transistors, which okay. هيك تمام؟ Okay. We have 6 IGBTs connected with a DC voltage source, which is considered as solar photovoltaic panels, entering as a DC, and output has 3-phase unfiltered voltage signal, enter an LC filter to produce a pure sinusoidal wave signal, and enters the grid we have. Here in front of us we have the synchronverter control system, which consists of 2 loops, the upper control loop and the lower control loop. The upper control loop, consisting of the reference active power that we hope to achieve, multiplied by 1 over omega n, the angular velocity of the virtual angular velocity of the virtual synchronous generator, and give us the mechanical torque, which enters the summation point here. And in addition to this term, we have another term called dP, which is the voltage group active power group control loop. dP enters in addition to torque mechanical, and the result of these would be subtracted with electrical torque that we I'll explain later. We have it from the control equations. Okay, the result of this summation point will enter an integrator 1 over S, and multiplied by the virtual moment of inertia, because the inverter is static, and we must behave like a real synchronous generator. And the result is omega, the virtual angular frequency. Okay, will also enters an integrator 1 over S to give us theta, and we enter it then with the reset point to compare it with the nominal rotor angle. Okay, the omega then will be subtracted by omega r. This is not theta, this is omega, and the result will be multiplied by dP. So the control equations I will explain later. Omega will enter the control equations to give us, in order to give us the electrical torque. In this equation, the electrical torque equals minus MFIF multiplied by the vector dot product between I, the three-phase current, and the sine tilde of theta. Now we will go to the lower control loop, which is the reactive power control loop and voltage drop control loop. We have Q set as a reference point, enters the summation point, in addition to the DQ, which is the voltage drop control voltage drop parameter. Okay, then the real Q will be subtracted from the summation point to give us and the result will be multiplied by integrator 1 over Ks to give us MFIF that we will need in control equations. Okay, to get the DQ, we will have to go to the synchronverter power circuit and take a feedback voltage signal and enter it with the amplitude detection tool to give us Vm, which will be subtracted by, which will be we will take the difference between the reference voltage and the amplitude that we obtained to give us dQ. Okay. Also, I would like to mention that the three-phase current feedback signal, we get it from the synchronverter power circuit to use it in the control equations. In addition to MFIF, here is the remaining two equations. E equals omega. This is theta dot is omega. Omega multiplied by MFIF sine tilde theta. This we will get the. This is how we get the electromotive force E. And the last equation is the reactive power equation, Q equals minus omega MFIF multiplied by the dot product between, or inner product of vector product between I and cosine tilde of theta. This is the system that is used in the study, which is IEEE 9-bus system. This is a single line diagram of the IEEE 9-bus system, consisting of 3 generators, 3 areas, and 3 buses, 5, 8, and 6 that consisting of the load. This is the simulation of the of this single line diagram on MATLAB Simulink. This is some of the results of testing the built IEEE 9-bus system, and this is the voltage and current signals for the bus 1 at the first stage. The first stage is the programmable voltage source stage. We use programmable voltage source instead of the real synchronous generator as a first stage of testing the system. This is the second stage of the same bus 1, that the voltage and the current is shown in the screen, and we obtain this result by replacing the programmable voltage source with a real synchronous generator, 3-phase. Okay. This is the summary for the results for testing the IEEE 9-bus system. We can see that bus 1 is 16.5, which is the I will tell you the theoretical values of the IEEE 9-bus. This must be 16.5, which is close, 18, 13.8, and 230 kV. This is for programmable voltage source, and this is for the real voltage source. We can see that it's close to the theoretical values, and this is what this is ensure that we build the system correctly. Now we will go to the designing of a three-phase of the PWM, pulse width modulation, that we use it in order to control the three-phase inverter with 6 IGBTs. We have three reference signals, signal A, signal B, and signal C, and we have a carrier signal that I will explain what is the function of this. If we take the first signal, signal A, and put it together with the carrier signal, and the difference between these two signals will be this diagram, and this is the diagram for switch 1 and switch 4 switching. We can see that if switch 1 is on, switch 4 will be off in order to avoiding the short circuit in the inverter. This is the result for the three-phase inverter. This is the unfiltered voltage signal, and after we enter these signals to the filter, we obtain the three pure sinusoidal wave signals. Okay, now this is the single machine infinite bus system. It is an emulation or a testing for the first stage for the IEEE 9 bus system, but the IEEE 9 bus system testing was in the real thesis, in the complete thesis. This is a paper from the thesis apart, and this is the first stage in testing the synchronverter, which is a single machine infinite bus system. We have three-phase real synchronous generator, a hydraulic turbine, and a exciting control, the field voltage control. Connecting with here's the grid, 230 kV, and here's a load. This is not necessary, but I put it in order to achieve another study. Okay, and this is the virtual synchronous generator entering a step-up transformer in parallel with the real synchronous generator. Here's the values that we put in order to testing the virtual synchronous generator if it is working or not. We put the reference active power 1000 watt, the reactive power 1000 var, the reference voltage 294 volt for the amplitude of the terminal voltage signal, and the virtual inertia 1.47 dp, the active power drop term is 150, and DQ 1, and the gain K we put it 74.06. These values are based on a real study or a reference that is mentioned in the thesis. This is the result for the synchronous generator for the single machine infinite bus system. We want 1000 watt for the active power, and we get 1000. For the reactive power, we want 1000, and we get 1000. For the frequency, we have 60 hertz. Here is the torque between 2 and 3, which is good, and here is the unfiltered voltage signal and the filtered voltage signal. Here is the reset operation. We integrate the output omega that I mentioned earlier in the control system, and the sawtooth signal when we enter to the reset toolbox, and omega phi that we use it in the control equations. This is the three-phase signals for the PWM, pulse width modulation, in order to control the switching of the inverter. And here is the conclusion. From the simulation results, it's clear that the operational output values of the synchronverter control system were the same as the reference set points, desired values, which means that the synchronverter is working correctly. Moreover, the values of the electrical torque and the filtered AC voltage signal are also the same as the theoretical values used in the simulation, which was 3 Newton meter for the torque and 208 volt for the filtered voltage signal. This confirms that the synchronverter is working properly. Thank you for listening.